Now what we're going to do is we're going to measure these things. It says add appropriate weights one at a time, about 100 grams. See how much it's suspended. In other words, you let it go. Don't make it oscillate. Just let it go so that it's stationary, so that it's in equilibrium, and see how much the spring is stretched. All right? If you know x, and you know, then it should correlate through fx equal to mg. So you do that for a few different weights, you plot it, and then you'll discover k, let's say, from that. Okay? B, spring elongation. Okay, it just says repeated for a coil spring, but that's the one that we're doing. We're not doing it with the rubber band. And plot mg versus y in number 5. Numbers in C, period of oscillation. What we're going to do is we're going to displace it a certain amount and let it oscillate up and down, count a certain amount of oscillations, and we're going to try to verify equation 16.3. All right, so we're going to change the mass and see if it matters. Now, one of the things that you're going to measure is how much you're pulling it down. You'll find that it doesn't depend on how much you're pulling it down. In fact, they do cancel out, the two effects. The more you pull it down, the stronger the spring force pushing it up. So it has to cover more distance, but it does so faster, and they exactly cancel out, which is very nice. And that's why you don't have the y in there. But you'll measure, obviously, the first section, you'll measure how much it goes down when you add a certain mass, and leaving it so that it stands still. Add another mass and see how much it goes down. Keep it still, and then measure that amount. Then you pull it away from its equilibrium position and let it oscillate up and down, and you measure the T, right? And you have the maximum amplitude because you know how much you pulled it away. You've measured K. You already know K from the first experiment because you measured mg equals Kx. And then you can compare what it should have been to what you. Okay, a pendulum consists of a bob, just a word that means this little mass hanging at the end of the string. Some of the physical properties or parameters of a simple pendulum are: 1, the length L of the pendulum, the length of the string in other words, or whatever it is holding it, the mass M, the angular displacement theta, and the period T. Period meaning how long it takes for it to complete one complete cycle. It doesn't matter from the top down and then back up to the top, or from the bottom part up, down to the side, and back to the bottom. However, one complete period. And that's what we're going to be measuring. Now, if the pendulum is swinging when there's no air, then there's no air resistance, there's no friction with anything, it'll just keep on swinging. If you hold it out and let it fall, it'll swing back and forth, up and down, back and forth, up and down, forever. Obviously, because there's air resistance, there might be friction in the string, and who knows what, so it'll slow down. But if you're assuming that even if there's air resistance, it's not so much that it'll slow it down tremendously so quickly, how would you measure the period? The period being one complete cycle. For example, you can measure 1/10 of the cycle and multiply it by 10, and that's the period, right? What is the best way of doing it? Best meaning give you the most accurate results. Using a long cord, using the angle, but we want to measure, let's say, given a certain configuration, we have a certain length, a certain angle, and so on, a certain mass. We want to measure now the period. We have a stopwatch or our own watch or whatever. What's right? You make many swings. Why? Whatever error you have, your reaction time or whatever, is divided out over 10 swings. So you have greater precision. Now, what's the problem with doing it over 10 swings? What's the potential inaccuracy that can come about?
Because when you swing, the distance is shorter.
What's shorter?
The distance covered.
Okay, if the air resistance is such that in 10 swings it's slowed down, then it won't. So you have to find some kind of a balance between one and the other. How many swings you know, right? And then you can first try it out and see if you think that it's slowing down, all right, or how many it takes until it slows down noticeably, and then decide based on that how many swings a day. You can do one measurement with 10 swings, one measurement with 20, and one with 30, and see if there's a difference or not. If there's no difference, then you know it's fine, it's okay, right? So all these just measurement and laboratory techniques to check your precision. What we're going to do is to try to find which parameters we can change and they won't affect, let's say, the time. Which parameters obviously do you know that we can change? For example, you change the color of the pendulum. change of the bob? Okay, why? What effect might there be if we change the shape of the bob?
Maybe just the mass or the air resistance?
Just the air resistance might be determined by the shape. If you have a sphere, it might be aerodynamically better than if you have, let's say, some flat thing like this moving against air this way, right? So obviously those things will matter, but only because of the friction of the air. But we choose a shape that at least will minimize friction, or we do it in a vacuum, right? What things might affect it, and this we discussed in a previous class, and we derived a little formula for small oscillations. If we want to check this formula to see if it's correct or experimentally to verify it, what would we do? What would we measure?
Angle.
Okay. Why would we measure? What angle? The angle like this. Okay, and why would we measure that?
Because it affects the time.
Because it's what affects the... Well, according to this equation, does it?
Yeah.
Does it affect?
Yeah.
In equation 3-2?
Yes.
How does it affect? All right. So for small angles, you get 3.2. Equation 3.2. You just get this. This times 1, or just this. For larger angles, you get this whole expression. So the first thing is, we're going to measure the angle, and we're going to see for smaller angles and for larger angles, does this equation really work for small angles, or do you need a larger equation? And does the larger equation really give us a more exact determination of t? Okay, given that we know the angle theta. So we're going to measure the angle. What else will we measure? We'll measure the length of the string. We'll measure the mass. We'll measure the mass, and just to find that it doesn't matter. It doesn't make a difference. If you keep the length the same, and gravity is obviously the same, and you change the mass, it shouldn't make a difference in the period of the string. Okay, so that's what we're going to do. We're going to be using these things over here with the string hanging on. Okay, and we're going to hang a mass on it. You have these to measure an angle. Okay, you just like hold it and kind of see where the string is. Measure the angle, and you'll change the length. You can make the string longer. You can make the string shorter. And you can put on different masses, and we'll just do a few quick measurements. We're not going to do it, you don't need the stopwatches if you do, let's say, 10 swings, okay? You just look at your watch with a second hand and measure it. Do one small angle, one medium angle, and a big angle, maybe 3 out of the 6, all right? And then we'll do 2 masses, maybe. So in experimental procedure, number 1, set up the simple pendulum arrangement. Number 2, experimentally investigate the small angle approximation and the theoretical prediction that the period increases with larger angles. Do this by determining the pendulum period for several angles in data table 1, keeping the length and mass constant. Okay. 3, experimentally investigate whether the period is independent of the mass. All right, using the 3 masses, whatever, maybe just use 2. We don't really need more than that. 4, experimentally investigate the relationship between the length and the period, using 5 different lengths. Again, we don't need 5 lengths. Use maybe 2 lengths or 3 lengths. No one spent too much time on that. 5, compute the theoretical period. Okay, that you can do at home. And 6, compute the percentage error between the experimental and the theoretical. Once you measure how much it is, you have the given. You know the length and you know the mass and you know the angle. You can use the equation, and you can also use your measurement. So you see how much difference there is between your measurement and the equation. Okay, and then obviously at home. Number 7, they're just saying that you do an experiment to find out whether an equation is valid. Once you know it's valid, you can trust it. Then, for example, if t is equal to 2 pi L over the square root of L over g, and you trust that equation, you can measure g, for example, right? What's the acceleration of gravity using L and t, once you trust that equation for small
Where do
angles.
you have number 7?
Page 43. The next page. I was reading through from 1 to 1 through 7.
Okay.
Okay, and then 8th is just a plot of L versus t squared. Okay. Okay, so if we want to measure the period, again, we're going to do the same thing. We don't want to do one period because it's too fast. We don't want to do too many because it'll slow down. We get some kind of medium range, and we can find that medium range by, let's say, taking 10 and 20 and 30 and seeing if there's a difference between them and so on. Okay.